We look into 5 lifetime distribution representations in this chapter. So far we have done the survivor function, the probability density function, and the hazard function. The fourth of the 5 lifetime distribution representations is the cumulative hazard function. The cumulative hazard function is denoted by capital H of t, and it is defined as the integral from 0 to t of h of tau d tau. You can think of h of t as the accumulated risk at time t. There is an analogy between the hazard function and its integral, which is the cumulative hazard function, just like there's a relationship between the probability density function and its integral, which is the cumulative distribution function. Capital H of t goes by an alias. Sometimes it is known as the integrated hazard function. All cumulative hazard functions satisfy 3 existence conditions. The first is capital H of 0 equals 0. That won't be surprising because if you look at its definition, when you integrate from 0 to 0, you will get no area underneath the hazard function. The second is, since the item is going to fail eventually, and again the item has lifetime capital T, in that case this cumulative hazard function has to eventually go to infinity. Finally, the last one, since you are integrating a positive function, that is the hazard function, I should be a little more careful there, the hazard function is non-negative, that means that h of t, capital H of t, is a non-decreasing function. 3 quick applications of the cumulative hazard function. It can be used in variate generation for Monte Carlo simulation. It can also be used to define certain distribution classes, and those distribution classes will be established as the last section in this chapter. And finally, when we get to chapters 7 and 8, you will see it showing up quite often in statistical inference. So that's the fourth of the 5, the cumulative hazard function. The last of the 5 is the mean residual life function. The mean residual life function L of t is defined as the expected remaining lifetime given that the item is operating at time t. And once again, the support on that is t greater than 0. So on the notes here, first of all, the mean residual life is the expected remaining lifetime, which is t minus t, given that the item has survived to time t, which is this condition towards the end of the definition. And if you were to put in 0 as an argument into the mean residual life function, you will get the unconditional mean of the distribution, and that is the expected value of t. So the expected value of t is a special case of the mean residual life function. Here is the derivation of the mean residual life function. This is the conditional probability function of the time of failure. Notice not the time to failure, but the time of failure of an item which has survived to time t. And all this is the probability density function evaluated at tau divided by the survivor function evaluated at t, and the support here is all values of tau which are greater than or equal to t. You can think of this 1 over s of t that you see in the conditional probability density function, you can think of that as a factor which forces this conditional probability density function to integrate to 1. So it's not a bad idea to integrate this function right here from capital or lowercase t to infinity and assure yourself that this thing in fact does integrate to 1, and it does. So if you want the mean of this conditional probability density function, that is this quantity right here. So given that an item has survived to time lowercase t, we want to know its expected time of failure, not its expected time to failure, but the expected time of failure. So that is going to be the integral over the support, and the support goes from t to infinity, of tau times the conditional probability density function d tau. You know that that conditional probability density function is just this from the line above, and so that's just the integral from t to infinity of tau times the conditional probability density function d tau. But that's not what we want. For the mean residual life function, we do not want to know the time of failure. We want to know the expected remaining lifetime, or the expected time to failure of the working item at time t. So here is L of t. By the definition on the previous slide, it is the expected value of t minus t, given t is greater than or equal to t. And that's going to be the integral from t to infinity, this time of tau minus t times that conditional density d tau. When you distribute the tau right here and the t, you'll notice that t is being multiplied by f of tau over s of t over its support, so that's just going to integrate to 1, and that's going to leave you with a t right here. The other piece you can do less with, that's just going to be tau times your conditional probability density function. One last thing, this integral is with respect to tau, and because of that, s of t is a constant, so that s of t can come out front here, 1 over s of t. Here is the integral, and finally minus t. So this entire equation right here is the way that you find the mean residual life function given the probability density function and the survivor function. Mean residual life functions have to satisfy 3 existence conditions. Here they are. The first one says L of t is greater than or equal to 0. You cannot take a working item at time lowercase t and say, oh, the expected time to failure was 3 minutes ago. Impossible. It's got to be greater than or equal to 0. The second, and we'll see this in an example subsequently when we deal with discrete supports, L prime of t is greater than or equal to -1. This function cannot decrease any faster than a slope of -1. That's the fastest it can decrease. And then the last one, the integral of 1 over L of t has to be infinity. If it satisfies those 3 existence conditions, then it's a legitimate mean residual life function. Here's an example. The exponential distribution is defined by a survivor function that looks like this, where lambda is a positive scale parameter, and it's usually called the failure rate. So the probability density function is the opposite of the derivative of the survivor function. So when you differentiate this survivor function and negate, you get lambda e to the minus lambda t. Once again, the support is t greater than or equal to 0. Now at this point, we'd like to use the formula on the previous page, and here is the formula that we derived in order to find the mean residual life function. So the first thing you do is you take 1 over the survivor function. Well, if this is the survivor function, then its reciprocal is that. You want to integrate from t to infinity of tau times f of tau d tau. So that simply gets copied down here, replacing t with tau. And then finally you want to subtract t because this is the mean residual lifetime. Well, if you use integration by parts on this, and I won't go through the details, but this is the integral right here that requires integration by parts, everything drops out and you get 1 over lambda for t greater than or equal to 0. What that says is, regardless of how old the item is, the mean remaining lifetime is always 1 over lambda. Now that should not be surprising to you because the exponential distribution has the memoryless property, and because a used item is just as good as a new item, it makes sense that you should get a constant for the mean residual life function. Furthermore, since you know that L of 0 is the same as the expected value of t, and you know for an exponential random variable the expected value of t is 1 over lambda, this result is also not surprising. Unfortunately, this 5 by 5 matrix is cut off here on the slides, but in the book you see it all the way out to the right. This is a from to matrix, and so what we're doing here is we're saying that we are going from this lifetime distribution on the row to the lifetime distribution on the columns. This is another way of saying once you have one of these lifetime distribution representations, then you can get to the other 4. So as an example, let's say you have the survivor function and you would like to get the density function. What this says is just take a derivative and negate. Likewise, if you know what the mean residual life function is and you'd like to know what the hazard function is, all you have to do is in the numerator take 1 plus the derivative of the mean residual life function and then divide by the mean residual life function, and that will get you the hazard function. So all of the relationships are in there, and it allows you to go from one to another. Here is an example. Given that h of t is equal to 2t, we want to find f of t from the h of t, f of t element. So f of t is h of t times e to the minus integral from 0 to t of h of tau d tau. And that formula right there comes from the 5 by 5 matrix that we had on the previous page. So we're trying to go from h of t to, starting with h of t, you want to go to f of t. So that is where that formula came from right there. And h of t in this case is 2t, so our h of t goes right here as 2t, and then h of tau goes right here, and that's 2 tau. The integral of 2 tau is tau squared. When you plug in the limits, you get negative t squared in the exponent, and here is the probability density function of a random variable with h of t being 2t. This happens to be a special case of the Weibull distribution with a scale parameter of 1 and a shape parameter of 2. Here are some final notes on the 5 lifetime distribution representations that we cover here in this chapter. Keep in mind that there are more than just these 5. There is the cumulative distribution function. There is the mean residual life function. There is the Mellon transform. There's all kinds of them. First of all, we are only looking at non-repairable items, which means they go from state 1, which is operating, to state 0, and then at that point they are discarded. We are doing that for now, but when we get to Chapter 6, we'll look at repairable systems. Second, threshold, warranty, and shift and guarantee parameters, like W, allow you to change the support from, instead of going from 0 to infinity, now they will go from W to infinity. So W stands for warranty, and what it does is it shifts the distribution so that rather than it starting from 0, it starts from W. So if you have a product that has a 90-day warranty, then W would be equal to 90, and the distribution would shift to the right. And so from the consumer's point of view, there are going to be no failures prior to time 90. Here's the strategy going forward. Step 1 in what we're going to do is, if we want to know about a lifetime distribution, we're going to collect data. After we collect data, we might draw a histogram if we don't have any censoring to the data, and we're going to take a guess at what the distribution is. Well, in Chapter 4, we go through a number of distributions such as the exponential and Weibull. If you can't find a good distribution that fits the data, then you may want to take a non-parametric approach, and that's out there in Chapter 10. Next, after you guess a distribution, you fit that distribution. So in Chapters 7 and 8, we use maximum likelihood to fit the distributions such as the exponential and the Weibull. Then, if there are covariates to be incorporated into the model, then you incorporate those covariates in using a probabilistic model, which is described in Chapter 5, and the fitting will occur in Chapter 9. At that point, you assess the fit of the model, and Chapter 11 is where we look at goodness of fit tests, and then finally you draw inference and take action. Most of the distributions that we encounter do not have a bathtub-shaped hazard function. For example, the exponential and the Weibull and the gamma distributions do not have a bathtub-shaped hazard function, even though that's mentioned quite a bit in reliability.